Before specifying your next architectural solar project, I invite you to gain a deeper understanding of photovoltaic technology and how it may influence the architectural design process. When you complete this core segment, you will understand how solar modules are constructed, understand the differences between the two main types of PV technologies, and know how to select the best means of integration and technology based on application constraints. A solar module is an assembly of components designed to produce power when exposed to sunlight. Its purpose is to offset energy consumption. By gaining a glimpse into a PV module's constituent parts, the ways in which solar panels can be leveraged as building components will become more clear. Most, if not all, solar modules consist of 5 to 7 parts, and their construction methodology is very similar to safety glazing. The front sheet can be made of glass or a polymer. Traditionally, front sheets are 2 to 4 millimeters in thickness and made with tempered glass. A front sheet's thickness enables impact protection at the cost of weight and efficiency. All solar modules feature solar cells. Those solar cells can either be deposited on glass directly or suspended within a laminate between two layers of encapsulant, as seen here. It is important to note that the addition of solar cell technology does not make architectural glass weaker. If anything, it may achieve greater strength because of the requirement to add an encapsulant to form a laminate. Thin film solar cells typically are applied to surface 2 of a front sheet, and a single layer of encapsulant is then used to adhere a back sheet and seal the solar cells from the environment. Crystalline silicon solar cells require 2 layers of encapsulant because they are made of brittle crystalline silicon wafers. The back sheet that encloses the package can be either glass or a polymer. Traditionally, an aluminum frame wraps the edge of the solar module to protect it during the installation process, add additional moisture protection, as well as providing a standardized means for mounting. That frame can also be adhered to the back of the module or not be present at all, should the mounting means accommodate frameless glass. The junction box is typically adhered to the rear side of the module, or in the case of some frameless modules, on its edge. The junction box features a positive and negative connection that enables stringing multiple modules together in series. Before we go too deep into all the integration opportunities, let's take a deeper look into solar cell technology. The two primary types of commercially available photovoltaic cell technologies are crystalline silicon and thin film. The crystalline silicon manufacturing process dates back to the 1950s and underpins all modern electronic technology. The silicon manufacturing process yields standalone circular silicon wafers cut from a larger cylindrical crystal. Wafers are processed into solar cells and individually laid up and electrically connected within solar modules. Crystalline silicon solar modules range in efficiency from only a few percent to approaching 23% today. The range is largely based on individual cell efficiency and the density in which they are spaced. On the left side of the efficiency spectrum, there are perimeter integrated PV technologies that place high efficiency solar cells orthogonal to the glass edge, collecting light via a directional film. If those same cells are placed at a low density in their typical form factors, efficiencies in the 11 to 19% range are common. High density crystalline solar technologies, with cell spacing at its absolute minimum, will range in efficiency from 17 to 23%. Modules that feature white substrates enable a higher degree of light to be reflected in between the solar cells to the surface of the glass and then back into the cells. The white substrates also help the modules operate at cooler temperatures. This is why the highest efficiency modules tend to have white backsheets. When it comes to thin film solar cells, they are typically produced directly on the glass that encapsulates them. The result is a significantly thinner solar cell that is typically about 30 times thinner than a silicon cell. Historically, thin film efficiencies have lagged behind crystalline, but cadmium telluride modules have approached a 20% efficiency and are becoming more cost-effective to produce domestically. Some manufacturers offer a range of absorber thicknesses and opacities should designers want to tailor the visible light transmittance to their application. This is a big differentiator for thin film technologies. It should be noted that as technologies become more opaque, their efficiency increases. This is why translucent thin film technologies lag so far behind high-efficiency crystalline technologies. Bifacial solar cells are solar cells that can capture sunlight from their front and rear sides. Both crystalline silicon and thin film technologies can be bifacial. Bifacial technology optimizes energy generation, particularly in environments with high albedo surfaces. A white roof or snow would constitute a high albedo surface. Black asphalt would be considered a low albedo surface. This is a benefit because bifacial solar systems can capture more sunlight from diffuse and reflected light, in turn, increasing their overall energy production. As manufacturing capacity has increased for these types of solar cells, they have reached cost parity with single sided solar cells. This trend has led to the increased availability of modules that filter light and can be recognized from below, a welcome evolution architecturally. The modules that dominate the solar market today are frame solar modules. This is mainly due to the standardization that their mounting methodology provides, the reduced risk of breakage during shipping and installation, and the edge protection from moisture intrusion. Module frames are typically aluminum and vary in height from manufacturer to manufacturer. The rear side of the module frame typically features various mounting holes, but those holes are regularly neglected when they are concealed in such a way that makes them inaccessible, such as in flush mount installations. In those instances, clamps are typically utilized to fasten the top of the module frame to a racking system. Frame modules can be roof applied and roof integrated when their racking system enables them to replace a roofing material. In overhead applications, it's preferable to utilize a method that can be accessed from below because walking on solar modules should always be avoided. Frame modules can also be integrated into visual or physical barriers in aesthetically pleasing ways when vertical surfaces are the best option. Frameless modules can also be roof applied with a clamping methodology like frame modules, although there are fewer racking products available today for this type of installation. The most common use of frameless modules is when the frame is less necessary, such as in the use of roof integrated solar shingles. In overhead applications, frameless modules offer the benefit of a lighter and less obtrusive architectural appearance. Frameless PV glass is regularly utilized in more standard integrated applications that leverage standard glass mounting means, such as glass railings or curtain wall framing systems. The critical difference between framed and frameless technologies is that the solar industry has developed an extensive supply chain for frame module mounting, whereas frameless products typically require either that the module manufacturer provides a proprietary racking solution or a compatible glazing framing system be identified. Next, I would like to dig into how slope glazing requirements can play a role in standard photovoltaic installations. The International Building Code, Section 2405, is devoted to slope glazing and skylights. Overhead solar, as seen here, would fall into this classification. Section 2405.2 discusses allowable glazing materials and states that as long as laminated glass is utilized with a PVB or equivalent interlayer, screens are not required under sloped glazing. Most standard solar modules meet the equivalence test outlined within the code, but it is the design professional's responsibility to ensure that overhead modules are compliant. This requirement should not be confused with safety glazing, since its intent is limiting the risk of falling glass. Safety glazing, on the other hand, takes things one step further and ensures that glass can resist human impact. In the instances where safety glazing compliance is required, stronger glass or encapsulant can be specified. In the case of thin film technologies, annealed glass is typically utilized for its flatness. When thin film technologies require safety glazing equivalents, one strategy is to sandwich that annealed glass in between two tempered glass lights, creating a tri-laminate, as seen here. If you are needing to conceal wiring in more integrated applications, edge-mounted junction boxes can be utilized rather than the traditional junction box that is mounted to the rear side of the module. Physical barriers are one form in which PV modules will need to resist human impact. It is critical in these applications that you specify modules that meet safety glazing requirements. To take the technology one step further, manufacturers can integrate those laminates into an insulated glass unit, also known as an IGU. Insulated glass units are two or more layers of glass that are separated by a spacer that forms an air gap to add insulative properties to glass. PV laminates can be integrated into an IGU by forming its outboard light. Envelope integrated vision glazing applications offer the best opportunity to apply solar technologies to large glass areas. Most technologies available today can be integrated into vision glazing, but it's difficult to identify ones that meet vision glazing's strict aesthetic requirements. Currently, there are several technologies being developed that are focused on addressing this expansive market opportunity with more aesthetic solutions. Slope glazing can be an obvious fit because it can be more optimally oriented. In both vision glazing and slope glazing, solar technologies can be leveraged to reduce solar heat gain, just like a frit pattern or a low E coating would. Spandrel glazing offers an opportunity to integrate higher efficiency opaque technologies and make a sizable impact on a building's energy performance. Since spandrel glass tends to conceal floor partitions or structural columns, it lends itself to concealing required balance of system components such as junction boxes or conduit runs. Now that you have a better understanding of how modules are constructed, the technologies they can utilize, and the different methodologies of integrating them, you should be able to identify more opportunities to make generating assets out of architectural surfaces.